Math 265A, Cuesta College. I'm Joe Vasta, and today we are going to cover 3.5 Derivatives of Trigonometric Functions. So just for the sake of this page right here, I'm going to let S equal sine x and C equal cosine x. Okay, just want to make sure that you guys are very familiar with these trig identities here. The tangent x is the sine over the cosine. Now we can also write the tangent x as 1 over the cotangent x, but I'm just writing things in terms of sines and cosines. The cotangent x is cosine over sine. Secant is 1 over cosine. The cosecant is 1 over sine. And here's an important identity right here. Sine squared plus cosine squared equals 1. So what we're going to be doing is we're going to be taking derivatives of the trig functions. And the one that we're going to start with is sine. So we want to figure out what the derivative of sine is. The first thing I'm going to do before we actually do the formal proof on PowerPoint is take a look at the graph of sine. There we go. So there's the graph of sine. So look what I have here. I'm going to do something that I have not done in lecture. I have a graph, and I'm going to guess the derivative, and I'm going to put the derivative actually on the same graph. Okay, so that's the part that I haven't done before. And this is just a guess here. But I'm going to start off right here at x equals pi halves. Okay, and the reason I start there is because when I draw the tangent line right there, I see that the tangent line has slope 0. So if I'm graphing the derivative, when I get to x equals pi halves, the point is going to be 0. Now, if this is a little too much for you, you might want to skip ahead in the video. Other places where the derivative is going to be 0 happen to be right here, which is 3 pi over 2. That's very small font. But oh well. And then also negative pi halves. Look, the slope there is 0. It looks like the slope is 0 at negative 3 pi over 2 as well. So the slope is 0 on this sine graph at the top of the hills or at the bottom of the valleys. Okay, now look what's going to happen. I'm going to estimate the slope at this point at x equals 0. So you have the point 0, 0 on the graph. And estimation's kind of, I mean, it's good and it's also bad because it's not really precise. But there's the tangent line right there. And so, like, what is the slope of that tangent line? Well, it looks like the slope of that tangent line is 1. 1 over 1. And once again, this is the problem with estimation, but let's just do this, because all we're doing is taking a guess on this piece of paper here. So the slope at 0 is 1. I'll put a dot right there. And with the same reasoning here, we can go over to x equals pi and draw a slope. It's hard to actually look at a line and say what is the slope without grid lines, but it looks like it's a negative, and maybe it's 1 up and 1 to the left, so that's negative 1. So the slope at pi, I'm going to take a guess at negative 1. And then the slope at 2 pi looks like it's going to be 1 again. And the slope at negative pi, so that looks like it's, we'll just guess negative 1. Look at these dots here. Dot, 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 dot. We're trying to guess the derivative. Look at that. What does that remind you of if you were going to connect a nice continuous curve? This, okay, let's connect it. Let's do it. And all we're doing is just taking a guess here. Oops, I missed the point. So when you miss a point in math, you just make the point bigger, and then it looks good. So look at that. That red graph looks like a trig graph itself. And so our guess, so we're just guessing here, is y prime equals why that looks like the cosine x. And so that could be the case where the derivative of sine is the cosine. Now if you kept taking derivatives, look at this. You took the derivative of the red thing, you'd probably get another wavy graph that gets shifted over pi halves. Again, just like the red one looks like the black graph that is shifted over pi halves to the left. So this is probably a good guess. We're going to turn it over to PowerPoint, where we'll do the actual derivation of the derivative of the sine and the cosine. So we're going to do a derivation of the derivative of sine and then the derivative of cosine. But before we do the definition of the derivative, we need some machinery. We need some help. And you'll see we have to start right here. Let A be the area of the sector. What the sector is this slice of pi. Okay, so that sector really is not a triangle. It's a sector, and we have to figure out what the area is. Well, the area of the sector, we can get at it by writing these proportions here. The area of the sector over the area of the circle equals, so we can set up this ratio over here, the angle of the sector divided by the angle of the circle. Well, we know the angle of the sector is theta. We know the angle of the circle is 360 degrees, but we'll use 2 pi. The area of the sector, that's what we're trying to get. That's A. And the area of the circle is pi r squared. So let's put all that information down. And then the question is, can you solve for A? We'll multiply both sides of that equation by pi r squared. A pi will cancel, so you won't even see a pi in the formula. The area of that little piece of pi up there is r squared theta over 2. Now you might have remembered this from another class. If not, that's all right. We're going to use this to get the next thing. Okay, so some of you actually might want to just skip ahead. You might not want to watch the proof of the derivative of the sine and the derivative of the cosine. Okay, we're going to continue. So we're going to hopefully remember this, r squared theta over 2. Okay, so now look at this. We have a pretty complicated picture here. And the first thing to notice is that I put the unit circle there. So the unit circle has radius 1. That's going to be important. Now I drew some triangles. So I draw a right triangle here. And so we actually have 2 triangles. We have triangle, well, we actually have more than 2 triangles, but the ones I want to focus on are AOB. AOB, that is not a right triangle. It's this triangle here, AOB. And then we say that the area of AOB is less than the area of the sector. The sector actually includes this little slice right here that I have the blue dot on. So that's why we have the area of the sector is greater than the area of AOB. And then what's greater than that is the area of the right triangle COB, which sometimes I'll call just COB. Okay, so that's what we have here. We have this set of inequalities. Now, before we move on, I'd like to know the length of this little dotted line. Well, I could say that the sine of theta, so I'm looking at this right triangle now, the sine of theta is opposite over hypotenuse. So the sine of theta is opposite over the hypotenuse is 1 because it's a unit circle. So sine of theta is opposite over hypotenuse, or we could just say opposite over 1. The sine of theta of that little triangle is the opposite. So this opposite side can be labeled sine theta, and that's what I'm going to do. Okay, now let's take a look at this big right triangle. Okay. I'm going to label side BC. So I'm going to use the tangent of theta. Now I'm looking at this big right triangle. The tangent of theta is opposite over adjacent. Tangent of theta is opposite, the adjacent is 1 over 1. Tangent theta is opposite over 1, or tangent of theta is the opposite. Tangent theta is the opposite. So I can label BC tangent theta. For some of you, that might be the worst part of this PowerPoint, is when we did that. Okay, let's go ahead and figure out what the area of AOB is. AOB, now that's not a right triangle, but the area is going to be the base times the height, or 1/2 base times height. That's what we really should have said. So 1/2 base is 1, because that's a unit circle. So 1/2, 1 times sine theta. So let's just write this all down. I'm going to write it all down. The area of the sector, remember the area of the sector is r squared theta over 2. Well, r squared, that's 1 squared because we have the unit circle. So that's the area of the sector. And the area of that big right triangle called COB or COB is 1/2 base times height. 1/2 base is 1 because we're on the unit circle times the height, which is tangent. So we have this right here. So let's write this, simplify some things here, make it look prettier. Sine theta over 2 is less than theta over 2 is less than tangent theta over 2. I'm going to multiply this inequality by 2 over sine theta. Sine theta is positive. So that's not going to flip those inequality signs. And what I'm going to get is I'm going to get 1 less than theta over sine theta less than 1 over cosine theta. How did I get 1 over cosine theta? Well, the 2's canceled. Tangent really is the sine over the cosine. So the sines are going to cancel and you'll have a cosine on the bottom. Okay. What I'm going to do is I'm going to take the reciprocal of each of those 3 things. So I'm going to go 1 over 1, and then I'm going to flip the theta over sine theta. So it's going to be sine theta over theta, and then it will be cosine theta over 1, and that will actually flip both of the signs. So we have that. See, I flipped the inequality signs. Now I'm going to just pick up this 3-part inequality and then throw it back down on the table. And I want the cosine on the left side, so it will say cosine theta is less than, and so this is what it looks like. Cosine theta is less than, sine theta over theta is less than 1. Okay, so for this works for our theta between 0 and pi halves. I'm going to replace theta with negative theta. Okay, so this is the result we want, but we wanted a little bit more. So I'm replacing theta with negative theta. And we have this right here. Now, because cosine has y-axis symmetry, or sometimes we say that's an even function, this cosine negative theta is just going to turn into cosine theta. Sine has origin symmetry, which means it's an odd function, so sine of negative theta is going to become negative sine theta. This is what we end up getting. Those two negatives in the middle will just create a positive. And now we have this thing that we developed. We've proved it for angles theta between negative pi halves and pi halves, where theta does not equal 0 because you would have a 0 on the bottom. So some of you might be saying, well, Joe, how is this getting me the derivative? Well, we're still working on it, okay? So the next thing I'm going to do is going to put the stuff that I have boxed at the top of the next slide. So there it is. That's what we proved. Now what I'm going to do with this three-part inequality is I'm going to throw a limit in front of each of those expressions. So I have the limit of cosine theta as theta approaches 0 is less than the limit sine theta over theta as theta approaches 0 is less than the limit of 1 as theta approaches 0. Well, we know this one right here doesn't have any thetas in it, and so the right-hand side is going to say 1. The left-hand side, well, the cosine of theta is 1. So I've got those guys right there squeezed. I've got this function here, this limit here, squeezed between 1 and 1. So by the squeeze theorem, I end up seeing that the limit of sine theta over theta as theta approaches 0 is 1. I'm still not ready to do the derivative, the definition of the derivative. This is quite a long proof. Okay, here's the next slide. Now, for some reason, I want to take the limit of cosine theta minus 1 over theta as theta approaches 0. Okay, so how am I going to do this? Well, if I put 0 into this, I'm going to get 0 over 0 because cosine 0 is 1. 1 minus 1 on the top is 0 and 0 on the bottom, so that's not cool. What I'm going to do is I'm going to multiply top and bottom of that fraction by the same thing, which would be a cosine theta plus 1. So on the top of the fraction, I get a difference of squares, and when you multiply that all out, you end up getting cosine squared minus 1. And on the bottom, I kept it the same. Now, we know that sine squared plus cosine squared equals 1. Okay, that's an identity that we should know. So the top can get replaced with a negative sine squared theta. You can write that down off to the side and verify that I'm correct on that. So that's what I'm going to do. So we have this limit now. Now we know that the limit of a product is the product of the limits. So I'm going to write it like that and just break that sine squared into sine times sine and then put the negative on the second one. And look at the first one. Look what we have here. We have our result, which should be a 1. So this first part's going to become 1. And the second part, the limit of negative sine theta over cosine theta plus 1, well, as theta goes towards 0, well, sine of 0 is 0. So you have negative 0 on the top. And on the bottom, you have cosine 0, which is 1. So you have 1 plus 1, which is 2. So you have 0 over 2 on the bottom. So this limit that we're interested in becomes 0. So we have two important limits, and these limits are going to come up when we do the definition of the derivative. Now, this was quite a lengthy derivation. You're not going to have to do this on the test or in the homework, but this is just for all you math purists out there who want to know why things are true. So let's go to the next slide where we start doing what we wanted to do right from the first slide, but we couldn't. Okay, so I have my limits here, and you're going to think that this is really beautiful. What's going to happen? I'm going to take the derivative of the sine. How am I going to do that? I am going to do the limit as h approaches 0 of the difference quotient. So that's what it looks like. So I put sine theta in the difference quotient. Then the next thing I'm going to do is I'm focusing on the top of that fraction. The top of that fraction has a sine x plus h. Now, if you had a trigonometry class, you probably learned the additive identities for sine. And so maybe you can just look that up, you know, sine a plus b or sine alpha plus beta, depending on your trig book. So I'm just using an identity right here. Okay, what I want to do next is just some simple algebra. I want to rearrange the second and third term on the top. So I want to put the negative sine theta first, and then the cosine x sine h third. Well, when I said first, I meant right here. I want to just switch these two guys. So when I do that, that's really not that much. I have this. Now, the first two terms on the top, they both have a sine x in common, so I want to factor that out. So I did that. And the third term, I just kept by itself. Now, I'm going to split this into two fractions because they both have h as the denominator. So that's what I've done right here. And the limit of a sum is the sum of the limits, and the limit of a product is the product of the limits. So I'm going to do both of those things in one step. So I have that right there. And look, the ones that don't have h's in them, like this one right here, limit of sine x as h approaches 0, and limit of cosine x as h approaches 0. These are just going to be sine x, cosine x, because there's no h's there. And then the ones we have here are the ones in the boxes up in the top right over here. So this guy right here is going to become 0. And the one over here becomes 1. So what do we get? We get sine x times 0 plus cosine x times 1, which becomes cosine x. So we have just finished the proof of the derivative of the sine is the cosine. Let's go ahead and do the proof of the derivative of the cosine. Now, the reason we went through all this pain is so we can get a shortcut. That means when we do our homework and they say, what is the derivative of this function? It has a sign in it. We could just memorize the shortcut and say, oh, the derivative of sine is the cosine, and not have to go through this every single time. So the definition of the derivative with its difference quotient, it served its purpose. It got us a shortcut. Now the next one. Now for those extra motivated students, you might want to see if you can do this one on your own. It works just like the sine in some ways. You will use both of these, and you'll also use an additive trig identity. But for those of you who are just like, okay, let's just see it, I put the cosine into the difference quotient and hit it with a limit. So this is going to be very similar. I use the identity, cosine x plus h has an identity, and it's cosine x, cosine h minus sine x and sine h. I'm going to switch those two terms, so the negative cosine is the middle term then. So it looks very similar to the last thing. I'm going to factor a cosine out of the first two terms. So I have that. Then I'm going to break that fraction so it's a difference. We can do that because both of them have h on the bottom. And then I'm going to say the limit of a difference is the difference of the limits, and the limit of a product is the product of the limits. Do that. And then this looks almost the same as the other one. It's a little different. We have the limit as h approaches 0 of the cosine x and the sine x, so those are just going to stay cosine x, sine x. And then we have these guys right here. This guy right here is 0, and this guy right here is 1. So let's see what this gives us. So cosine x times 0 minus sine x times 1. The derivative of the cosine is not just the sine, it is negative sine. And so this completes our PowerPoint derivation, which went probably about 18 minutes on the PowerPoint. So now it's back to the paper. Okay, we're back to the piece of paper, and these are the things that we derived. The derivative of the sine is the cosine. The derivative of the cosine is negative sine. So what we want to do now is we want to find the derivative of the tangent. So how do we find the derivative of the tangent? Let's go ahead and do this problem. It's not going to be as bad as the other ones that we saw on PowerPoint. Well, the tangent happens to be, can we write this in terms of sines and cosines? The answer is yes. The tangent is the sine over the cosine. So when I go to take the derivative of the tangent, I could just take the derivative of this quotient. And so guess what I'm doing? I'm doing the quotient rule, where this is the top and this is the bottom. So y prime equals, so here goes the quotient rule. The derivative of the top is cosine times the bottom minus the top times the derivative of the bottom. The derivative of cosine is negative sine. This is all over the bottom squared. So cosine x squared. Okay, so what do we have on the top? We have cosine squared. Oh, by the way, when you have cosine squared, you can put the squared in between the s and the x as a superscript. And we'll probably do that. And we'll do it right here. Cosine squared is cosine squared x. And then we have a negative here and a negative there. That negative's a little smaller, so let me make it bigger. That's going to be a positive. Plus sine squared x. This is all over. On the bottom I have cosine squared x. Now, does the top remind you of anything? Cosine squared plus sine squared. Well, cosine squared plus sine squared happens to be 1. That's an important identity. So this is 1 over the cosine squared x. And if you remember, 1 over cosine is actually secant. So 1 over cosine squared is secant squared x. So it looks like the derivative, y prime, is the secant squared x. So we have that right there. So that's how you figure out the derivative of the other 4 trig functions. Well, here's the tangent. The sine and the cosine, those were tough. That PowerPoint presentation, that was a tough thing to look at. The only good that would do is if you were trying to go to sleep. You can just turn that on. You'll probably be sleeping before it's done. But besides that, I mean, it was pretty tough. Now, there are some people who want to become technical and they want to become math majors or engineers. Maybe they looked at it and they said, wow, that was kind of cool. But no one's going to say it out loud. So now we know how to find the derivative of tangent. Now, this is something that we have as another shortcut. So we're going to have shortcuts for all 6 trig ratios. In fact, let's go ahead and put up the next piece of paper. This one right here. And I kind of use crazy notation. I actually forgot to put a D right there. Okay. And we say the derivative of the sine is the cosine. The derivative of the cosine is negative sine. Now, I arranged them in a weird kind of order here, but on purpose. And then we just derive this. The derivative of the tangent is the secant squared. We just derived. So we've derived these 3. These guys right here. It won't be the first problems in your homework. It will be near the end. Those you'll derive in your homework. You'll actually derive these formulas. Now, how will you derive the formulas? Well, like for the cotangent, you'll write that as the cosine over the sine and do a quotient rule. The secant, you'll write that as 1 over cosine, and you'll do the quotient rule. And then same with this, you'll go cosecant is 1 over sine. So when they ask you to derive these formulas in your homework, you do what I did with the tangent. Now, these should be memorized. Okay, we're doing an online class, so you know, some of you are like, yeah, I'm not going to memorize them. But the deal is, when you take future classes, they're going to expect you to know these 6 derivatives. So let's just give you some ways of memorizing them. Okay? The derivatives of cofunctions. What are cofunctions? The ones that have cos in them. You have the sine, and then you have the cosine, and you have the tangent, cotangent, and the secant, cosecant. So the derivatives of the cofunctions are negative. Another way of saying that is d dx, and then there's a c there, and then the other ones, you get a negative number. And so that's one thing to remember, that if your trig function starts with a c and you take the derivative, the answer is going to be negative. Okay, here's another one that I found online. If you can spell secant like that, then you can take its derivative. And you're thinking, what? Here's the secant. Well, look at, if you can spell it, it has a secant in it, and it also has an ant. Okay, I know you're like, oh, there's an ant. That's disgusting or whatever. But rearrange those letters, and ant becomes tangent. So if you can spell secant, hopefully you can remember what its derivative is. And secant and cosecant say it's all about me. Okay, so let's talk about this. So if you had to memorize these in a future class, I've kind of broken these up into 3 groups here. Okay, so you have the sine and the cosine. And so the sine gives into the cosine. You know, when you take the derivative of the sine, there's a cosine. You take the derivative of the cosine, there's a sine. Of course there's a negative sign, but I'm not putting the negatives here. So they kind of feed off each other. These guys, you take the derivative of the secant. Let's look at this. You get, one goes back to himself, secant, tangent. You take the derivative of the tangent, it's secant secant, or secant squared, so they both go to the secant. Now I like this diagram because I'm a visual person. Some of you might think this diagram is confusing. But just like we have this interplay between the secant and the tangent, the same interplay is between the cosecant and the cotangent. The derivative of the cosecant, you have a cosecant and a cotangent. I didn't put the negatives here. So the cosecant feeds back to itself, okay? So, and then also gives to a cotangent. So there's the cotangent. But the derivative of the cotangent, both of them go to the cosecant, cosecant, and you get the cosecant squared. Actually, negative cosecant squared. So the only trig functions of the 6, when you take the derivatives, that have themselves within their derivatives happen to be the secant and the cosecant. And that's why I say the quote from them is, it's all about me. Because when you take their derivatives, they're always given a little something back to themselves. You know, like the secant, you take its derivative, the secant's still there. He's all like, it's all about me, I want to be in the show. And same with the cosecant. So those are the 6 shortcuts. Took us a long time to derive all that. Let's go ahead and do some of the kinds of problems you will see in your homework. And you know what the problems are going to say. The problems are going to say, find the derivative. And so let's see if we can find the derivative. There's the first one. And maybe with these problems, the more you can pause the video and work out the problem before I even start, the better it's going to be for you. You might say, well, I might end up getting the wrong answer. That's all right, but the fact that you're trying to do it means you're getting engaged into this, and when you go to do your homework, you'll be more efficient. So if you want, you can try to do this one. I haven't done anything with the product rule yet, but let's go ahead and take the derivative. We have the product rule. So this is x times the cosine x. So there's the first, there's the second. I'm going to do the product rule. So the derivative of this function here, we say the derivative of the first, and I'll put parentheses around here, even though I don't really need that. The derivative of x times the second plus the first times the derivative of the second. What is the derivative of the cosine? Well, it starts with a c, so it's going to be negative. It's going to be negative sine x. And I couldn't imagine, like, anytime I had to take the derivative, like with something like this or the next problem, having to take out the definition and the difference quotient. I mean, it would take forever to compute derivatives. So let's clean this up. We have y prime equals the cosine x minus x sine x. And there's really nothing more you can do with that except put a box around it. There's the answer to problem number 1. Okay, let's go do another problem that's kind of similar. And so when you do your homework, all you're doing is using those shortcuts. So we have the derivative. We have to take the derivative. Oh, take the derivative of this function. The function is e to the x secant x. Okay, so looks like it's going to be another product rule. Here's the first. Here's the second. And we'll do it just like we did the other problem. So the derivative of the first times the second plus the first times the derivative of the second. So the derivative of the secant x, and this is something that you should try to memorize. It's the secant x times the tangent x. Okay, so let's clean this up. Actually, it would have looked good if I didn't put all the parentheses. Look, this is an e to the x. So I'm just writing this without the parentheses. And we have plus e to the x. And then we have secant x, tangent x. Some of you are saying, well, can I factor out an e to the x? Sure, go for it. Knock yourself out. You can also factor out an e to the x secant x, and that could be outside, and then you would have a 1 plus tangent within the parenthesis. But it's all the same. There's no simplification that can go on. So there it is. Let's go ahead and do some more problems. So I would say the worst part about this lecture was the derivations. Here's problem number 3. Find the derivative of this function. Well, now we have a quotient. There's the top. There's the bottom. Consider pausing the video and seeing if you can do this one on your own. Okay, so we have the derivative. So I'll go ahead and verbally say what I'm going to do, but I'm not going to write like f prime and g and all that stuff. So here it goes. To take the derivative of a quotient, you start off with the derivative of the top. The derivative of the top, That's 1 minus sine x. Okay, the derivative of 1 is 0. The derivative of negative sine x, well, it's going to be negative cosine x. Why? Because there's a negative there, so that just stayed there, and the derivative of sine is the cosine. So let's go through our little saying here. The derivative of the top times the bottom minus the top times the derivative of the bottom. The derivative of the bottom is cosine x. And you might be wondering what happened. The derivative of 1 is 0. The derivative of sine x is cosine x. So that's going to be all over the bottom squared. So it looks like I have some distributing to do. So this equals negative cosine x minus cosine x sine x. Okay, and then also I'll be distributing a negative cosine x into that. So watch this. This is going to be minus cosine x, okay, because I'm multiplying that yellow part by 1, and then I'm going to go negative cosine x times a negative sine x, which is going to be a positive cosine x sine x. This is all over 1 plus sine x squared. Can we simplify the top? Yeah. Those guys are opposites. They're out of there. And the top now has 2 of these creatures, or actually negative 2 of them, minus 2 cosine x. And on the bottom we have 1 plus sine x quantity squared. Now we can multiply out the bottom. That's really not going to help us simplify this fraction. Nothing is really going to cancel. So we're done. This is a good enough answer. There's the derivative. So I've boxed just that right there, which is alright, or I could have written y prime equals that. That's also acceptable. We have just found the derivative, and it would be hard to imagine doing these problems using the definition and the difference quotient, limit as h goes to 0. These things would take many pieces of paper. So now we have shortcuts for the 6 trig functions, and that's all 3.5 is about, the shortcuts of the 6 trig functions. Let's go ahead and do another problem here. With the last problem, let me just mention one thing. Some of you might have said, oh, Joe, we should have just canceled the signs. You can't do that because you have 2 terms on the top and 2 terms on the bottom. The only time you can cancel with fractions is when you have 1 term on the top and 1 term on the bottom. And so, you know, I forgot to mention that at the beginning of the problem. Like, you cannot cancel those signs. You know, so I've seen, okay, so I'm going to show you what I've seen on a test before. I've given a problem that was very similar to this. And hopefully that student isn't watching this video. But if they are, why are you watching my calculus video? You've already taken it. Okay, so what they did is they went like this. They canceled the signs. Okay, this is bad. I'm going to actually put an arrow pointing to this with the word bad. And then they went ahead and they canceled the 1s. And so I remember just like seeing on the answer line, because that's what I looked at first. And they're like, okay, there's the answer. Whatever, okay. I think this was the result of something, and so that was should have just written that, and then they wrote like minus divided by plus. Okay, so this is bad. Okay. Unless you're a math terrorist, then this is something that you would probably do to create terror in other people. You would say, hey, imagine if you were a math terrorist and at the same time you were teaching math. Just think of how much damage you can do. And if you had tenure, oh man. So let's go do this. So why did I bring up that other one again? It's because I know some people might be thinking, hey Joe, let's cancel those x's. No, don't do that, because this x is part of the argument of the tangent. So there's no way you can cancel them. Unless, of course, you were a math terrorist, and then, of course, you're not doing math anymore. You're just, creating terror. So how am I going to do this problem? I'm going to do this problem like I did the last problem. So pause the video and see if you can take the derivative of the tangent x divided by x cubed. Maybe you're having a hard time getting started there. That should clear things up. Okay, so here it goes. I have to take the derivative of a quotient. So I'm going to use the quotient rule. The quotient rule says the derivative of the top, which is secant squared, times the bottom, x cubed, minus the top, tangent x, times the derivative of the bottom. The derivative of the bottom is 3x squared. This is all over the bottom squared. So we have that right there. So let's go ahead and clean up the top a little. We have an x cubed. We usually like to put those in front of the trig functions, and then we have secant squared x. And then I have minus 3x squared tangent x. This is all over the bottom, which is x to the power to a power is multiply x to the 6th. Okay, so some of you are like, well, let's box the answer and move on to the next one. Well, let's see if we should. Can I factor anything out of the top? And the answer is yes, I can factor out an x squared. Each of these two terms have an x squared in common. So I'm going to do that. X squared. So in parentheses I have x times the secant squared x minus 3 tangent x. This is all over x to the 6th. Now I have one term on the top. And you might be confused because you're like, well, there's two terms within the parentheses, but the big picture is one term on the top, because it's this times this, and one term on the bottom. So I can cancel. There's two x's up here, which are going to cancel with two of those 6 x's. So I'm going to put a 4 there. So my final answer is going to be this. I'm going to write it out again. There's really not much more I can do. X times the secant squared x minus 3 tangent x all over x to the 4th. Now if you're thinking you can factor out that x, you're wrong, because that x here and that x there, those are arguments of trig functions. So you can't factor them out front. And you can't cancel the x to the 4th with that x. That's another thing some people want to do, because now you have two terms on the top. Terms are separated by pluses or minuses, and so you can't cancel that. The only way you can cancel this is like what we did. We factor something out. So this is the final answer. As the season is changing, I'm doing my notes in the same spot that I was always doing them, and it seems like the sun is getting closer to my area because I have the curtains open. And I'm pretty sure in a month, if I'm still doing these, I'll just have sun in my eyes, and this will be completely sunny, and it might be too bright for the camera or whatever. I don't know what will happen. So we'll just take it day by day, I guess. Gotta do another problem. So we're going to change the problems a little. Here's the next one. The next one tells us to find the second derivative of the cosecant. So you might consider pausing the video and seeing if you want to do this. Okay. To find the second derivative, you must find the first derivative. The first derivative is just using the shortcut. And right now you might not have memorized these because you're seeing this for the first time. But the derivative of something that starts with a C is negative. And remember, it's the secant and the cosecant who like to scream out, it's all about me. And so the derivative of this guy is this guy, cosecant x. Cotangent x. Okay, so there's the first derivative. They ask us to find the second derivative. So that is what we're going to do. To find the second derivative, it looks like we have a product here. So perhaps we should do the product rule. Okay, so here is the second derivative. The product rule says, this one has a negative in front of it. So it says the derivative of the first. So the derivative of negative cosecant. So the negative's right there. The derivative of cosecant is negative cosecant x cotangent x. Okay, so there's the derivative of the first. Times the second plus the first times the derivative of the second. Now the derivative of the cotangent, we have that, we wrote that down. This is a shortcut. It's going to be negative because it starts with a C, and then we have cosecant squared x. So let's go ahead and clean this up. This second derivative, there's two negatives there. So it looks like we'll just write a positive. And we have a cosecant times a cotangent times a cotangent. So this is cosecant x cotangent squared x. Then I have two negatives here, which become a positive. And I have a cosecant times a cosecant squared. So that's going to be a cosecant cubed. Now, I can factor out a cosecant. You can do that if you want. You don't have to. There's your answer. And let's just remind you that, like, if you have, let's just talk about sine. Sine squared x. That does not equal the sine of x squared. Okay, so, you know, don't be confused by this. This really means, so this one right here really means the sine, and the argument is x squared. Okay, parentheses are optional on the argument when it only has one term. This one over here is really the sine times the sine, or the sine x quantity squared. So this probably came about through laziness. People didn't always want to put the parentheses up, so they just put the 2 there and said if the 2 is there, we know that I'm going sine times sine. And then if the 2 is right there, I know that this is really sine of x squared. Let's go ahead and do another problem. Our next problem we're going to do is a little different than the last one. It's problem number 6. Let f of x equal x minus 2 cosine x. Find an equation of the tangent line at x equals pi. Wow. So this is crazy because it has trig in it and it has x values of pi instead of nice numbers like 7. So how do you find the equation of the tangent line? To find the equation of the tangent line, you need the slope of the tangent line. To find the slope of the tangent line, you need the derivative. So pause the video and see if you can do this. The derivative of f of x. F prime x equals. The derivative of x is 1. And then we have minus 2. Then the derivative of the cosine is negative sine. Okay, so it looks like the derivative equals 1 plus 2 sine x. So you want to find the slope of the tangent line at x equals pi, so you're going to put pi into this derivative. So I have 1 plus 2 sine pi. So if you are considering sine of pi, I'm just going to put the sine graph here. It goes like that. And I know this is very small, but there's pi. The sine of pi is 0. So this is really 1 plus 2 times 0. Now a lot of people, instead of drawing the sine graph, they would just pull out their calculator and do sine of pi in their calculator. With these lectures, I always try to do everything by hand unless I absolutely need a calculator. Now, all you purists out there will go, yeah, I like that. So the answer is 1. For what? This is the slope. Okay. We also have a point. They gave us the x value of the point, which is pi. What is the y value of the point? Well, how do I find the y value of the point? I put the x value not into the derivative, but into the original function. So f of pi is pi minus 2 cosine of pi. Okay, so I'm going to draw this one. This one right here was the sine. This is the cosine. The cosine goes like this, does one full cycle like in 2 pi. So this is, instead of me reaching for a calculator, I can do this without a calculator. The cosine of pi is this down here, negative 1. So what do I have? I have pi minus 2 times negative 1. Or this is going to be pi plus 2. And that's what goes right there. Pi plus 2. So I have a slope, I have a point, so that means now I can try to find the line that has the slope and the point. Lines look like this, y equals mx plus b. I just have to find the constants m and b, and I have the constant right here. M is 1. So y equals 1x plus b. Let's figure out what b is by plugging the points into that. And I am running out of space on my paper. I think I can make this. So the y value is pi plus 2. the x value is pi, and we're trying to solve for b. I subtract pi on both sides, so I end up getting 2 equals b. So I have the b value. So now this line that says y equals x plus b, now I know that my final answer is y equals x plus 2, and I finished the problem. Okay, we're done, and what I'm going to show you is some visual satisfaction on this. Here's the function, which looks weird. I'm going to show it to you, and then I'm going to put the point on the function, which is this point pi plus 2, and then I've graphed y equals x plus 2. We're going to see what it looks like. So there it is. Here's your original function right here. This is f. So that's what x minus 2 cosine looks like. Looks like that. Just looks like you're climbing the hills there. And here's pi. Maybe I should make this one bigger. This is pi. So here's the point right there. The y value of this point is pi plus 2, which it looks like it's 5, but it's not 5. It's going to, pi plus 2, 3.14, so it's going to be 5.14. So yeah, it's a little above 5. And there's the tangent line right here. This tangent line is the one we just found. This is y equals x plus 2, has slope 1, has a y-intercept of 2. Looks like that. It also looks like that this line, this is just my guess, I could be wrong, it almost looks like this line is the tangent line at the x value negative pi, and perhaps at this x value here and an x value up there. So you don't have to actually generate graphs on a computer, but there it is. Now in your homework near the end, like problem number 78, you're going to be matching graphs with their derivatives. So be prepared to see something like that near the end of your homework. Let's go ahead and do problem number 7. What happens, okay, so this is a weird kind of problem. So this is just an exploration problem. What happens when you keep taking the derivative of y equals sine x? Let's do it. Y equals sine x. Y prime equals the cosine x. Y double prime equals, okay, so these are just shortcuts I'm using. Derivative of the cosine is negative sine. Y triple prime is, well, the derivative of sine is cosine, but there's a negative there, so this is going to be negative cosine x. The fourth derivative, remember that notation there? So we don't want to start putting 4 tick marks. I've seen some books put Roman numeral 4 up there. What is wrong with those books? I want to find the authors and slap them in the head. So maybe they're Romans. Okay, so what is the derivative of the cosine? It is negative sine, but there's a negative as well. So you're going to have 2 negatives that cancel out, and look what the fourth derivative gives you. Sine x. So then the fifth derivative, let me just put this in a different color. So this right up here is the fourth derivative. And then if you take the fifth derivative, you get the cosine. And the sixth derivative, you get negative sine. And the seventh derivative, you get negative cosine. And then guess what? The eighth derivative will bring us back to sine. So that is very weird or familiar. There's 2 things we want to point out about this. Okay, so what happens when you keep taking the derivative of a sine? It's a 4 cycle. Okay? That means there's 4 states in the cycle. You know, sine, cosine, negative cosine. First, let's look at the graph and then we'll mention something else. Look, when I took the derivative of the sine, I got the cosine. And then I take a derivative of this. We said that the graph shifted over pi halves. Well, if the graph shifts over pi halves again, it gets me this graph right here. Which, if I drew the whole thing, it would look like the original sine that got reflected through the x-axis, which is the negative sine. Okay? And then if I shift that graph over pi halves, then I get something that looks like this. And it actually is the cosine that gets reflected through the x-axis, so that's negative cosine. Now, if I happen to shift the blue one pi halves to the left, look what I end up getting. I land right back up on top of the sine, and that's what happens. That's why when you take 4 derivatives, it starts off here, and then it goes here, and then here. It's like a wave, and then up here it comes again, and there it is. And so that's a cycle of 4. Of course, this makes great singing in the car. You know, sometimes people sing in the car. Well, now everybody has devices, so who needs to sing in the car anymore? But, you know, like you see some people, they're like, oh, when we get bored, we sing 100 bottles of beer on the wall. Well, this is a funner song. It's the derivative of sine song. Kind of forgot the melody, but it goes something like, you know, the sine, the cosine, the negative cosine, you know, you throw in derivatives and you just keep going in cycles of 4. Okay, so there's the application. Now, the question is, have you seen something like this before in your life, in your math life? And the answer is yes. You don't have to write this down. Where have you seen a 4 cycle? Powers of I. I to the 0 is 1. I to the 1 is I, the square root of negative 1. I squared is negative 1. I cubed is negative I. And then what happened with I to the 4th? Well, that's I squared times I squared, which brings you back to that. Here's I to the 5th. Some of you did not want to see this because you're like, oh, I hate imaginary numbers. And then I to the 8th. I want to make sure the video is still playing because it's been known to shut off. Make me mad. Okay. So, I want to also point out something. That this guy right here, you know, y equals sine x. It's not, we wouldn't call that the derivative. Here's the first derivative and the second derivative and the third derivative and the fourth derivative. Okay. But sometimes, and we won't do that this much in this class, so I'll put it down here. Sometimes the original function is called the 0th derivative. Okay. And so we don't usually say that, but there are some times where I have called the original function the 0th derivative, especially if we're putting things in summation notation. So that is problem number 7. Now what I want to do is I want to do problem number 54. Problem number 54 is in your homework, and you're supposed to derive the formula for the cosecant. Now the formula for the cosecant, I'll tell you what it is. It's negative cosecant x cotangent x. So we're not supposed to use the shortcut. We're supposed to derive this and not really going back to the definition of the derivative. What we want to do, okay, so let's just write this out. Y equals cosecant x. We want to write this as 1 over the sine x, and we'll derive the formula. So I believe, I don't know how they say it in the homework, but we're going to derive the shortcut. So this will be the fourth one that we derived in this video. So how do I derive this? I use the quotient rule. There's the top, there's the bottom. Okay, the quotient rule says the derivative of the top, it's the derivative of a constant, times the bottom minus the top times the derivative of the bottom. The derivative of the sine is the cosine. This is all over the bottom squared. Okay, so let's see what we get here. This is 0. So on the top I have negative cosine x all over sine squared. And I'll write the squared like that. So it seems like, oh, well, we've got the derivative of the cosecant, and that is the derivative of the cosecant. But we want to derive the shortcut, which is the derivative of the cosecant is negative cosecant cotangent. So how am I going to do this? Well, I'm going to continue. The rest is just some trig. I have negative cosine on the top. And on the bottom, I end up having, what, sine x times sine x. So the question is, what is the cosine over the sine? Well, that is the cotangent. And the other question is, what is negative 1 over sine x? Well, negative 1 over sine x, 1 over sine is the cosecant, so this is going to be negative cosecant x. So we have just derived the shortcut. The derivative of the cosecant x is negative cosecant x cotangent x. Now, when they say derive the shortcut, you know, that's what we did. But for the most part, if you're doing your homework and cosecant is in there, just go ahead and use the shortcut. Use the fact that the derivative is this. So this completes 3.5. Do your homework. Have a good day. I'll see you in the next video.